All right, we're on to our last segment of the packet. That would be about inductors. So we're going to start by defining inductance. Then we're going to put inductors in circuits with resistors and then capacitors. So to begin, we're just going to define an inductor. So a capacitor is a component that stores energy in its electric field between plates. Inductors store energy in the magnetic field of a coil. So what do inductors do? Inductors resist changes in current. So if we think about what an inductor is, which is a series of coils, inductors work by trying to maintain their flux. Because if you change the current through a set of coils, you're going to get an EMF induced to try to create that current to fight the change via Lenz's law. So an inductor is really this device that is opposing current changes. So we said inductors don't mind currents, they just get angry at changes in current. So inductance is sort of like inertia or mass, but in a circuit. So as a result, the energy formula that we derived for the energy stored in an inductor, and I actually think I'll use L. No, I'll use B because it's the magnetic field. The energy stored in the magnetic field of the inductor is 1 half Li squared. Notice that this is super similar to kinetic energy, right? Because inductance is sort of like an electrical inertia or mass, and current is a rate of change, just like velocity. So that's a good way to remember that formula, although it is on the sheet anyway. What is the expression for EMF across an inductor? So the definition of inductance kind of helps us here. So we can define inductance by the fact that the EMF induced across an inductor has to be related to the current change, but we know that inductors oppose changes in current. And how good is an inductor at opposing that current change? Well, that's our proportionality constant L. So that's how we can sort of rationalize this formula, right? The EMF induced is going to oppose a change in current, and this L represents sort of the efficiency at doing that. So a pretty standard example would just be given some sort of current function, and you got to find the EMF induced. The current through an inductor with inductance L varies according to I equals B times T. Derive an expression for the EMF induced. Well, we know that the EMF induced is just negative L di dt, although it's very rare that this negative sign has any meaning. The inductance was L, and we're just taking the derivative of our current function, which is B times T. So we get negative L times B. Or just L times B, because usually we're just asking what is the absolute value of the EMF induced. But realize this EMF is induced to try to fight the increase in current. All right, now we have an alternate way of defining inductance, just like we can define capacitance as the amount of charge you're able to store per unit of potential difference. Inductance can be defined as the amount of total flux that can be stored in your inductor per unit of current. Because, of course, if you increase the current, you increase the B field, which increases the flux. But not all coils are created equal. So this sort of determines how tightly packed your B field can be inside of the coils. So we also have this relationship that inductance can be defined as capital N times the flux through one coil divided by the current I, where capital N is the number of total coils you have. The only inductance we have to be able to derive in E&M, although it's on the formula sheet, is that of just our classic ideal solenoid. So that means we're going to plug into this formula. So we need to just know the total flux through a solenoid. So to do that, we are of course going to need to know the field. And this is a known result. The B field inside an ideal solenoid is mu naught because it's air filled, little n times I. But I don't really like this form of the solenoid equation. It's always appeared on my formula sheets as not little n, the turn density, but actually what that means. So the turn density of the solenoid, little n, is how many coils you have per unit length. Because it makes sense that the field shouldn't be stronger just for having more coils. It should be stronger if you have more tightly packed coils. So this is our known expression for the B field in a solenoid. What's the total magnetic flux through the solenoid? Well, we know that the total flux should just be N times the flux through one coil, because I have capital N loops. So I just take the flux through one loop. And flux is just going to be BA, because the B field is perpendicular to all of the coil areas. And we know what B is. B is mu naught times N over L times I. And then our area was just A. You can imagine there exists an alternate world where you're just given the radius, so you got to do like a pi r squared thing. But this would be mu naught capital N squared IA over L. So quite a lot of variables going on in here. So what is the inductance of the solenoid? Well, now it's really easy, right? You just got to divide through by the current. So L is just defined as N phi, which we just found, divided by I. So all I do is I just divide out the I from my total flux expression, and I get mu naught capital N squared times the area divided by the length. And this is actually on the formula sheet. People forget this, but it is. It's not often used, but it does appear on the sheet. Also realize that just like capacitance, the only way to change inductance is by changing geometry. So we can check mu, that is your permeability. So you could put a different material in there to increase inductance. Capital N is your coils. You can obviously change that. Area, coil area, you can change that. And L is the total length of the solenoid. So makes sense. We only get geometric quantities. There's no current in there. It's kind of the main thing that shouldn't be in inductance. All right, now let's put these things in circuits here. So in the circuit shown below, we close the switch. This is really similar to the RC circuit. I just replaced the capacitor with an inductor so we can see the similarities and differences. All right, so at short times, inductors say, oh no, you are not changing the current through me. So short times, we get a gap, right? A hole in the wire, because the inductor is very displeased that you're trying to change the current through it. So I'm just going to redraw my circuit. I'm going to kind of leave the inductor branch alone for a minute here, so I can shamelessly copy paste. Because I know I'm going to redraw it sort of for the long time case. Get that ready. So after a short time, it is a gap. So this is opposite to the capacitor behavior, right? So it is a gap in the wire, meaning no current can cross the gap. So if we color code the potential, we see that we don't get a short circuit. We get what we've been calling the long circuit, where you're just forced to go all the way around. I have to remember my colors, Roy. Yeah, I should do orange before yellow. So that's my potential. And notice that there's only one valid loop, right? Because the gap essentially just takes that part out. So I just have a giant series circuit to deal with. So REQ is just all of the resistance of the circuit. So 1, 2, 3, 4, 5, 6 R. And then that means my total current is just going to be script E divided by 6R. So we can go and actually fill out the table for this case right now. I think we'll do some solving out kind of on here, actually, then we'll translate. So we know that every single circuit element in here gets our same current of 1/6 script E over R. So that means this voltage drop, delta V, is I times R. So we have our I, which is 1/6 E over R, and then we multiply by R, so that just gets rid of the R in the denominator, so we know we're dropping 1/6 across this resistor, 1/6 of the battery EMF. We drop 2/6, which is a third, across this resistor, and then we drop 3/6, which is 1/2 across this resistor. And then because I know we're going to need it, the voltage drop across the inductor, well, this just follows Kirchhoff's loop rule, right? So notice I can go from the R resistor, then the inductor, and then I'm back. So this must be 5/6 to close the loop. And you can also check that it works by doing the other way, where I can see that this is an orange to blue potential difference, which I could have also found by doing the 1/3 plus 1/2, and 1/3 plus 1/2 is 5/6. You can check that. All right, so now we can just plug everybody into the table. So there's a voltage drop of 1/6 of the battery EMF. This was 1/3 of the battery EMF, and this was 1/2 of the battery EMF, because every single resistor received the same current because we were just in a nice single closed loop. And again, how do we know that? Well, we just know delta V is IR. Now pick your favorite power formula, because we know literally everything. But since we know current and voltage drop, just to avoid squaring anything, I just like power equals I delta V for this one. So 1/6 and 1/6 makes 1/36. Oh, sorry. Current through is 1/6 script E over R. I'm sure that bothered somebody, but we fixed it. So 1/36 squared over R. 1/6 and 1/3 is 1/18. And 1/6 and 1/2 is 1/12. And if you sum it up, the total power is 1/36 plus 2/36 plus 3/36, which is 6/36, which is 1/6 E squared over R, which is what you expect because the REQ of the circuit was 6R. Wow, quite the tongue twister. All right, now we'll deal with the inductor. So we said that based on the loop rule, if we form a closed loop with the R resistor, which is dropping 1/6 of the battery EMF, the remaining 5/6 must be dropped across this one, the inductor. Now, for the current change, we have the relationship that the voltage drop across an inductor is L di dt, up to a sine, of course. So we're just going to say this is absolute value. So I just need to divide the voltage by the inductance to get my rate of change. Then the current, well, this is a gap. So if it's a gap, you have zero current through your inductor, so you have zero energy stored, because energy is our kinetic analog, 1/2 Li squared. All right, now long time. The long time actually takes much less thinking, because after a long time, the inductor has succeeded in stopping the current from changing, but really the current has ended up winning because it has tricked the inductor to allow current through it. So after a long time, an inductor behaves like a wire. It's totally happy. So if we try to color code here, boom, boom, we see that almost our entire circuit is blue. So this actually means we drop the entire battery across just the R. And that shouldn't be surprising at this point, right? You know that when you have a wire behavior in your circuit, whether it be a long time inductor or a short time capacitor, you always get some sort of shorting in these compound circuits like this. So that just means our REQ is actually just R. So our current in the circuit is just going to be just the expected Ohm's law current. And it's important to note that that voltage drop only occurs across the R resistor because that is the only resistor with current. So I delta V gets us just sort of a definition here. No current, so no voltage drop across either resistor, so no power. Right, those are effectively removed. Seeing how the whole end of this circuit is blue, I can just remove it from consideration. Then for the inductor, well, the inductor is happy. There's no color change across the inductor because the current isn't changing. That's what makes the inductor happy. Now, there is a current through it, though, right? Inductors don't hate current. They just hate current changes. And if we look at our circuit, all the current is going down the inductor branch because that is a short. So all the current goes through the inductor. So the energy stored, which is 1/2 Li squared, is just 1/2 times L times E over R squared. So that's our sort of short and long case analysis for the inductor circuit. Now we're just going to mirror what we did before with capacitors. So we're going to do our diff EQ. So we have an inductor with increasing current. We'll solve everything. And then we have our inductor with sort of decreasing current. So this is like I think I want to do the R first. Not that it matters. So this is our equivalent of like the charging RC circuit, where we're going to start ramping up current through the inductor. So if there's initially no current, the inductor isn't going to just allow that current to change. It's going to take time. So we actually know that if our current is initially 0 and it has to ramp up to some maximum value, it's going to be our sort of exponential approach function, which actually tells us what the solution is going to be, because we know that the curve that models this is going to look like I equals I max 1 minus e to the negative t over tau. Again, we need to know this. Like, we need to just memorize that this parent function and this graph are associated with circuit quantities that sort of ramp up and approach a maximum value. Now, we have to define what I max and tau are, of course. We'll do the diff EQ. We'll just do the diff EQ now. So for the diff EQ, we say always start from Kirchhoff's loop rule, which says the sum of the voltage drops must be 0. Drops and gains are in a closed loop. So I start at the battery. Always include a battery, even if there isn't one. It'll help you get the signs correct. Then I drop across the resistor. Then I drop across the inductor. Then I'm back. There is a battery, so I'm going to continue to include it. Then my resistor, voltage drop across a resistor is IR. Voltage drop across an inductor is LdI dt. No weird stuff with minus signs. We just take everything that is not a battery to be a drop. And, I don't have to do anything. I don't have to do anything to this, because there's no substituting needed, because I have I and a derivative of I in the same equation. So the only other thing to note is that, yes, we know this parent function is the solution, but these parameters I max and tau still need to be determined. I max, we know that after a long time, this inductor basically just becomes a wire. So after a long time, we just have a resistor in series with a battery. So we know that I max is just going to be the typical Ohm's law current, E over R. And then tau, for an LR circuit, is not LR, but it's L over R. And this is REQ. If there's a bunch of R's in there, you got to do REQ first. So that is the solution to the ramping up graph. Now, you can find this analytically if you do separate and integrate. Please don't waste your time knowing how to solve this diff EQ. If you separate variables, you can just spawn the solution in. So as long as you mess with this and like try to separate variables, and then you can just spawn this in. You don't have to deal with the integral or any of that. That is a skill I think we have, but you just need to be able to know this answer corresponds with this diff EQ. It's on my memorized list. All right, now we have the inductor with decreasing current. So this one is harder to like practically achieve. This would be some scenario where like you already have a current through the inductor, E over R, it says. At this time that you've just basically flipped a switch and you're just sending a current through the inductor. You'll see how this happens in like the two switch problem we're going to do next. So when we do this one, well, there's no infinite current source. So we know that this graph is going to be decay, right? There's only two circuit graphs you can reasonably get in E&M. I guess there's a third. If you have inductors and capacitors, you get sinusoids, but it's either a decay graph or it's an approach graph, and this would be a decay graph. So we already know what models this. This would just be modeled by I max e to the negative t over tau, with I max being the initial current, E over R, and tau being the usual L over R, as long as we're taking R to be REQ. All right, loop rule. So once again, we start by saying the sum of our voltage drops and gains is 0. We always include a battery until we remember there isn't one. And this helps you get the sign right. So again, this is my own invention. I call it the phantom battery. We always include a battery as our first line for the loop rule, and then we realize we don't need it, and it makes your signs work out every time. Now, what is the voltage drop across the inductor? Well, now we're just left with, well, we have 0 battery minus L di dt minus IR is equal to 0. Or you'd get L di dt equals negative IR. Or you could solve this and get di dt equals negative R over L times I. But to write this in time constant form, the time constant is actually just 1 over this value. So to see like why the time constant is L over R, you could write it like this. But that's not really necessary. I would actually just stop sort of right here. But this is just to show you kind of where that time constant comes from. All right, so that's everything with our transient L over R circuit. So what is the time constant of an L over R circuit? Oh, how topical. We just were talking about it. Tau is L over not R, but Req. So be careful of that. Now we have our classic 2-switch problem. So we're saying the switch is initially in position 1. What is the time constant of the circuit in position 1? Well, tau 1 is just going to be L over R. All right, what's the time constant in position 2? Well, so this is position 1. It's literally just a loop with a inductor and a resistance R. But now, if we flip to position 2, it's an inductance L with a resistance of 3R. So tau 2 is just going to be L over 3R. Very riveting. After the circuit has been in position 1 for a long time, the switch is moved to position 2. Derive expressions for each of the following. The initial current through the inductor. Well, we know that inductors maintain current at short times, at least. So if we are in position 1 for a long time, we know that current is going to be the Ohm's law current, E over R. And as soon as we flip to position 2, that inductor is going to maintain that current. So if we just draw sort of what was happening here, this is what we had originally, where we have this current, E over R, when we're closed to position 1. So that inductor is going to maintain that current for a short time. Because if we instantly just flip that switch on over to the other position, that essentially creates this circuit. And we know that inductors maintain currents at short times. So this current will stay E over R shortly. Now, of course, it's going to exponentially decay, but at least at a short time, it's just going to be the expected Ohm's law current, E over R. So what's the potential difference across the inductor? Oh, and just for more clarity, we'll show that this is like position 2. What's the potential difference across the inductor? Well, if we try to color code, so if we color code this, we see that our inductor, which is basically serving as a battery, right? Just like capacitors can serve as a battery, so can inductors if they're just unpowered and have current through them. So what we see is that delta V across the inductor is equal to delta V across the 3R resistance. And oh, how convenient. We know the current in the circuit, right? We said at short times, we should say this is the initial potential difference, by the way. At short times, we have a current of E over R, so we can just do our Ohm's law, our just standard Ohm's law. And this gets a result that people are initially puzzled by originally, because it seems like kind of illegal, right? Really? I got more voltage drop than the battery? Yeah, so inductors can actually create huge potential differences because they maintain currents. So the inductor did not ask the resistance, what current do I supply? The inductor had a current through it, and it maintained it, and it told the resistance, oh, you got to deal with it. This current is coming. I don't care what you do with it, but it's coming. Then you can just solve for the rate of current change through the inductor, because we know that the EMF across an inductor is negative L di dt. So that means the absolute value of the potential difference is equal to L times the absolute value of di dt. So we just solve for L, for di dt. So the absolute value of di dt would just be the EMF across the inductor divided by the inductance. And we said that was 3 times the battery EMF. So this is kind of an interesting one. Definitely an interesting problem. All right. Last but not least, we have LC circuits. LC circuits are tough, but they don't show up very often. There's a lot of cool stuff with them, though. All right, so at each time, we're saying we have a charged capacitor that has and zero current in a circuit at t equals 0, and we're gonna close a switch or something. So maybe I'll draw it like this to show like the L, then the C. So again, we have an LC circuit, right? That is an inductance and a capacitance. And I actually don't like this picture. I don't like my inductor. That's better. All right. So we're just going to look at the sort of different extremes of the LC oscillator. So I'm just going to do a paste, 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 and paste. Great, lovely, shameless. And we have these sort of 4 or 5 key times here. So first it says the capacitor is charged and there's no current. So that means we have an E field between the plates. Then we have a discharged capacitor, which means the positive charges would have left the plate to go this way. So we have a current, but no charge. Then if we think about what's going to happen, that means this charge is going to wrap around, and the positives are going to hit the other plate now. Oh, so this means that we're going to get a magnetic field. We're going to get a magnetic field around the solenoid. And I think we want the B field actually that way. Yeah, because of the closed loop. Then we have a charged capacitor once again, except this time the field is flipped. Then we have a discharged capacitor, which means the charge is flipped, kind of going the other way now to discharge. And then lastly, our capacitor is going to charge back up again. All right, so here are the key times. Here are the key times we're looking at. So again, what does this LC oscillator do? Well, we have charge stored on the capacitor. Then current, so energy stored in the electric field of the capacitor. Then the discharging capacitor sends all its energy to the magnetic field of the inductor. Then the inductor charges the capacitor back up the opposite way. Then the capacitor discharges, sending a current through the inductor the opposite way. And then we're back to where we started. So this is all just a perpetual cycle because if there's no resistance, no energy is lost. So if we draw our bar chart here, we're going to have our energy distribution. Here we're going to have some energy that can be stored in the electric field, and then we can have some energy that could be stored in the magnetic field at these various times. And you already know what's coming. I probably should have just prepped this ahead of time, but you know, hindsight is 20/20. So there's our charts. Okay. All right, so at this time, well, all of my energy will be stored in the capacitor. So I have all my energies in the electric field of the capacitor, no energy stored in the magnetic field of the inductor. Now we have traded. I have no energy stored in my capacitor's electric field, but all of the energy has gone to the inductor in its magnetic field. Now I've charged the capacitor the opposite way. Doesn't matter that it's charged the opposite way. It's still storing energy. There's still no current there, so no magnetic field. Then okay, cool. The current has reversed in the inductor, but there's no charge on the capacitor, and then we're back to where we started. So we see this is just kind of like your middle school energy skate park idea, right? Where you can just keep trading back and forth of the energies. So this is why we'll always solve LC circuit questions with energy, unless if we're asked about like the period. So if you want to solve for any like circuit quantity, like charge or current, you're probably using energy. So here, the energy stored on the capacitor. So it's 1/2 Q squared, and we'll call this Q max over C. That is one of our energy storage formulas in a capacitor. What's the energy stored in an inductor? Well, this would be 1/2 L I max squared. And then, watch this move, a double copy paste. Look at that, so skillful. So our energy expression is capacitor, inductor, capacitor, inductor. So a lot of these circuit problems just involve setting these two equal to each other. Just like if you have a mass spring system, you set your max kinetic equal to your max elastic potential. So those things all work for us nicely. Yeah, that's kind of our big qualitative overview of the LC. Now we're going to go on to some quantitative things and get into the weeds a bit with the diffeq. All right, what could the charge on the positive plate look like on the capacitor as a function of time? Well, we would assume that maybe let's pick the top plate in my diagram here. Well, I'd start with charge on my positive plate. Then I would become discharged. Then I would charge up, but the opposite way. Then I would discharge again, and now I'm charged back to where I started. So we can see that this is going to be a sort of sine curve, or cosine curve rather. So we can continue this for another cycle if we wanted to. So this looks like some sort of like cosine function. Then what could the current in the circuit look like consistent with our graph of Q? Well, if we think about this, here we'd have sort of no current initially, right? We're given that there's no current initially. Then we had maximum current, and knowing that I is a derivative of Q, we see that we have zero slope kind of at these maxima. Then we'd have maximum negative slope, then zero, then maximum positive slope, then zero. So I need to go 0, negative, 0, positive, 0. 0, negative, 0, positive, 0. So we see we get this sort of sine curve, and this would be negative sine of omega t. Now, of course, you could have defined your current direction differently, and now we'll try to somehow pretend that I graphed this correctly with my freehand. And of course, one of my lovely techniques, in addition to copy pasting, we have make the point so big that you can't tell when I do stuff wrong. Wow, look how perfect that was the whole time. Lovely. All right, now let's come up with the loop equation for the LC circuit. So this is no different than anything we've done before. It's just going to take a different form because we'll see when we try to put the derivatives together, it's going to become second order. So we always said that we start with the sum of the delta V's equals 0. We gain some voltage across the battery. Even if there's no battery there, we always include one. Then we drop some voltage across the inductor. Then we drop some voltage across the capacitor, and then we're home. Now we remember that there's no battery. voltage drop across an inductor is L di dt. Voltage drop across a capacitor is Q over C. And this is differential, but not the differential we're looking for, because we don't have Q and its derivative. We have Q and I's derivative. So we can write this as negative L times the derivative with respect to time of I minus Q over C equals 0. But what is I? Well, I is dq dt, right? I is dq dt. So I'm just taking a derivative of the derivative of Q, so that is a second derivative. So if we solve this for the second derivative, we get d squared q dt squared equals negative 1 over LC times Q. And I thought it was important to solve this for the second derivative because this is a very special form of a diffie-q in physics, where you can't solve this by differential equation in your usual like separation technique. This is because it's second order. And you start to run into issues because the answer is not just going to be e to a regular type of number, because I can't just take a derivative twice and multiply a number by itself twice to get a negative, a real number at least. If you know, you know. But you know the answer has to be something like this. So this is a well-known equation known as a simple harmonic oscillator. So using your differential equation, figure out the angular frequency and period. Well, let's do that. So the angular frequency, well, we have to recognize that a simple harmonic motion follows this form that says the second derivative is equal to a negative times a constant called omega squared times x. So we can just match things up here, because we said that d squared q dt squared is equal to negative 1 over LC times q. So what that means for us is that omega squared is equal to 1 over LC. So that means omega is equal to 1 over square root LC. And we also want to find what's called the period of oscillations. So what is omega? Well, omega is angular velocity. So omega is defined as angle per time. And if we wanted to relate that to the period, well, in one cycle t, you would have swept out an entire unit circle, 2 pi worth of angles. So this tells us that capital T would be 2 pi over omega, which means that the period is just 2 pi divided by 1 divided by square root LC. So we get a 2 pi, and then the double division pops up to the numerator. So we get this result. 2 pi square root LC. And we'll drag everybody over a bit so we can see better. All right. This is given on the formula sheet. And if you look hard enough, you can find this in the mechanics section. It's there. All right. So determine an expression for the charge on the top plate of the capacitor. Well, if it's simple harmonic, we know the answer is going to be sine or cosine. So based on our graph, our Q function is going to be, we'll call this Q of T, is equal to Q cosine of omega T, right? Because it was maximized. It was maximized at the beginning. This is just a regular old cosine curve. And omega for an LC oscillator is 1 over square root LC. It's not square root LC or LC. You get that denominator in square root. So our charge on the top plate of the capacitor as a function of time is modeled by this function. Let's find the current consistent with this. Well, we just know that I is dq dt, so we can just take the derivative with respect to time of this function. So we get to practice our trig derivative and our chain rule. So we get q is not involved. Derivative of cosine is negative sine. which is what we expected when we graphed our curve, remember? And then derivative, we got to use the chain rule, right? So the constant is 1 over square root LC, so I got to multiply by that. So we'd get Q over square root LC times negative sine of T over square root LC. And you can also check by energy conservation that I max and Q max should be related like this. All right, lastly, we are going to solve, just doing energy stuff. All right, what is the energy equation for an LC circuit? What are the special cases? Well, we know that the total energy in an LC circuit is the energy stored by the capacitor at any given time plus the energy stored by an inductor at any given time. But this is incredibly annoying and just not useful to us. So we zoom in on the extremes. So if all of your energy is in the capacitor bucket, we can write this as 1/2 Q squared over C, as long as we're using the maximum charge on the capacitor. Or we could put all of our energy in the inductor bucket and deal with maximum current. So this equation is true at all times, and we have two special cases below it. All right, we got charge Q initially. We want to solve for the maximum current and the period and the frequency. Okay. Max current. So we should just set our energy, max energy in the E field equal to max energy in the B field. So if I can store a charge Q as my maximum charge before current starts to flow, that means Q is the max charge on the capacitor plates. And then magnetic field, the energy stored there is 1/2 Li squared, as long as this is the max current. Goodbye 1/2, so we get Q squared over C equals Li squared. So we'd get I squared is equal to Q squared over LC. So we get the expected result. There's a reason I did this. We get I is equal to Q divided by square root LC as the maximum current. So maybe I'll reattach the max subscript here. So again, notice that agrees with this, right? We use trigonometry and derivatives to get the max current as our amplitude over there. This is an alternate way, the better way of getting max current. All right, what's the period of oscillations? Well, by definition, period is 2 pi divided by omega. So T is equal to 2 pi divided by 1 divided by square root LC, and we just essentially derived that expression again. Now, what's the frequency of oscillations? Well, also connecting to mechanics, if period is how long it takes for every cycle to be completed, frequency is how many cycles can be completed every second. So frequency is defined as 1 over period. So you can just flip this upside down. Another way of doing this is omega is also defined as 2 pi f. So you could just divide the 1 over square root LC by 2 pi to get this. So this is like the hertz of your circuit, the cycles per second. All right, after what, like 7 videos, we have finally done it. Crushed the entire E&M course. So again, you have pretty much my guarantee that no item you're going to see is not at least a descendant of one of these packet items. So there we go. We can consider E&M conquered.